Great. So second lecture on linear systems, Fourier transform, things like that. We're going to continue in that vein today. And this is like, a two-lecture introduction to a full year course in signals and systems, right? If you really wanted to know this stuff very well, you would take a second year double E course in signals and systems, something like that. And normally it's time domain signals and frequency components and such. So we're doing a crash course in how this, sort of formalization of signals is used to describe CT, MR, and other imaging things. And one of the key concepts is on this page right here, which is looking at an image. So I have a field, it's a square here, and I can produce an image by adding up different sinusoids, different plane waves of different frequencies and different amplitudes. And so what is a plane wave? In the plane in our image, here's a collection of plane waves, right? And they're essentially encoded or described by a sine function or a cosine function, usually the sum of the two, where as we move along in space, we roll through that sine wave, and depending on we're going to say this is usually the k value, the k vector, the spatial frequency, will experience different frequency oscillations as a function of position, right? And so by changing these two parameters, mu naught and mu naught here, which will soon be kx and ky, we can change the orientation of that plane wave. In order to have a more general set of functions, I mean, if all you have is sine waves, there are various limitations to that, obviously. For example, when x and y are 0, you always get the value of 0. So you need a complete set of functions to produce a complete set of values in the plane. And what's done is we create a exponential or a complex notation where we have a position in the plane is a complex number, and it's a cosine wave plus j sine some argument. Okay, so now we actually have for each position in the plane, we have a complex number. So that will give us both an amplitude and a phase at each position, right? So looking at how we're going to mathematically formalize the input-output, relationships between the object we're imaging and the image that we produce, right? So I have a set of signals here. It goes through our detector, and then we produce some image. And then we're going to use this system function here. In the textbook, he uses this script S notation. I don't have that in PowerPoint, so I'm going to use just a bold S for the system. And basically what we're going to take is this mapping takes functions from 2D and maps them onto 2D functions. Okay, so it takes a function, makes a function. That's what it does. And we can define a system as linear if it follows this criteria. And if I take a set of functions, say in the XY plane, and one set of functions potentially is, we go back here, there's a set of functions. Okay, so I've got 6 different sort of functions sitting on the plane here. So, oops, I'm going the wrong way. Now I take a set of those, we had 6 just now, and I multiply each one by a specific weight, right? And then add them all up together. That is one method of describing how I'm producing my output, right? So I have these multiple inputs, I add them up together, and I get an output. And that's a description of this mapping function or the system function that makes the image. If this is true, this equation here, which means if I take each one of those individual functions and map it individually first, And then I add all of those up together on that side of the system's function, and I get the same answer as I did when I added them together in the spatial domain, then that system is called linear. Okay. And it's a very powerful limitation. If you say, I know my system function that's going to take the input and make output, that thing's linear, that is a constraint that is very powerful in terms of controlling the crazy mathematics we have to use to describe that system. Okay. Not all systems are like that, right? But if you have a class of systems that are like that, then you can do some very expedient mathematics on describing how things are going. So is that concept pretty clear there? You're gonna do problems on this. You'll be asked, like, here is a system taking, f of x into g of x. Is this system linear? That's good on your problem set, right? And so you have to plug it into this and figure out whether or not this relationship is true, right? So here's our system, script S or cap S as we're doing. We have an input, goes into the system, we get an output, okay? If recall back when we're doing this sort of heuristically, we say we just put a point here as our input. So I have a very small dot as my input, and I put it through the system and I get an output. That's called the impulse response function of that system. And that describes what the system does to a very small dot. And as you can imagine, any picture can be made of a bunch of dots, right? And so if you know how dots move through the system, that's a lot of information. In fact, it's kind of all the information you need sometimes. The more general notion of the impulse response function or the point spread function, those are equivalent things, is that if I move this dot to a different place in the field of view, and then I measure this point response, I will get a different point response. Okay, so it varies as I move around in my field of view. So on the edges of my image, maybe it's fuzzier or blurrier. The point response function is wider, right? And this is a common thing. If you have a cheap binoculars, right, and you're looking at right down the focal point, and you can see a boat, and it's really clear. And then off to the edge, if you don't move the binoculars, you just use your eyes and go to the edge of the lens field of view, and there's an equivalent boat there, and it's blurry, right? So the one out on the edge is blurrier than the one in the middle. That's a common phenomenon, right? It's the same thing happens in CT, right? Is that if you like go way out to the outside of the field of view, the resolution out there is going to change, right? Then straight in the middle of the scanner. In MR, not so much. So that's the impulse response function, point spread function, those are the same thing, very important concept. So here's our impulse response function, and we can write down how we produce an image. So this is the output of our system, G, X, and Y. That's our final picture as a function of 2 dimensions. And then this is the signal from which that we fed into our imaging system. Okay, so this is the perfect boat signal coming in as light waves, or the perfect brain in our MR scanner. And this is our description of what the imaging system does to this to produce our output. And we just multiply. So if I'm at a point in my field of view of my image, and I say, what's the value of my image at XY? I'm at a point right here. That value at that point is actually proportional to the entire input image, right? Multiplied by the point spread function. Okay, so the point spread function goes off over the whole field of view. We multiply it, integrate over the entire field of view, and that's my output. So essentially, the output is this weighted sum of all of the field of view that I'm looking at, right? If this function that I'm multiplying my input is very sharp and spiky, then that integral gives you essentially just what's around that location. And so you can forget about all the stuff everywhere else. If this function, on the other hand, is kind of broad, then the value of your image, right, is proportional to a very large field of view of signals coming in, right, from the object. So that's why a spiky point spread function or a very sharp impulse response or point spread function gives you very sharp pictures. Yeah.
Between the impulse response function and the Dirac delta.
Oh, an impulse response function that is a Dirac delta function is a perfect imaging system. So that means that if I have my input, and that's this f function here in 2D, and I multiply it by this and do the integral, if this is the Dirac delta function, it just brings out the value at that one point. It's not dependent on any values around it, right? So there's no blurring. So that's, if this was a Dirac delta function, you would have created a very good imaging system, right?
So the impulse response is kind of like, it can be like in a range between anywhere like the Dirac delta function and like an imperfect
right
system. Okay.
If we put as our input the Dirac delta function to test our system, right? So now f, this thing, we're going to put f as the Dirac delta function. So now my picture is just a tiny dot at some place, right? When I perform this, what I get out is this thing, right? If it's a Dirac delta function, then this image here is a delta function when it comes out. If this is not a delta function, say it's a Gaussian, which it usually is, it's sort of a smooth blobby thing. When this is a Dirac delta function and I perform this, gxy equals this thing, right? So you see the point spread function, what it is.
Our goal is like get the Gaussian to be a small series.
Ideally, for an imaging system, you want this function, which is the PSF, point spread function of the system, you want it to be really, really narrow, right? So it sifts out local stuff, right? Okay. If you can make the assumption, right, that this h function is not dependent on position, okay? So I don't have to pull down a new h function for every xy point, right? I can just use the same one for all xy points. Then, the system is shift invariant. That means its point spread function just doesn't matter where you are looking in your field of view. You're always going to get the same point spread function. And that, along with linearity, something that's shift invariant is another restrictive thing that makes life a lot easier when you're trying to use mathematics to describe the systems. So shift invariance means that the point spread function does not change as we move around with x and y. Now, this here, the semicolon. Oh, this, yeah, okay. That's a great question. So I should have pointed that out. This is not literally, it shouldn't be thought of as a four-dimensional function, right? It is essentially what this is for each xy, I pull down a different two-dimensional h of, say, sine eta, right? So it basically is saying, I've got a list of h of point spread functions that are 2D. And when I'm at a specific hxy point, I just pull that one down and do this integral, right? This is going to be convolution in just a second. You're looking ahead. Yeah, it looks like a convolution, right? Yeah, it's not a convolution yet though, right? What this is, gxy is just the input times this point spread function. Once we have this relationship that says, I don't care where the hxy is going to be the same regardless of what my xy position is, then you can write down the equation that looks like this, right? And that's a convolution.
Is different depending on which pixel.
Right, right. It has that dependence on xy. If it isn't dependent on XY, if it has just, if HXY shifted over X naught is the same as it is over here, then I can write it like this, right? And now that semicolon goes away, right? And now it's just a one function, right? And so now that I have this one function that's proportional to these two dimensions, right? I can perform this integral, right? In exactly the same way as I did the last one, except this time I put in x, y, and it just plugs in as the independent variable in the point spread function, right? And then we do the integral over the image itself, or I'm sorry, the input signal itself is going along, and whatever the point spread function is at that point gets multiplied, right? So this thing is a convolution. So we've taken our input signal, which is like the perfect image, and we have convolved it with the point spread function, and that gives us our output signal. Yeah.
It's H of X of the point spread function or the system?
H of X is the point spread function, which for these simple things we're saying is all you need to know about the system in terms of its spatial resolution, right? So they are kind of equivalent, right? The system is actually the integral, right? So it's like that's how you turn input into output, is that integral, right? H of X is the point spread function or the impulse response function. Okay, so now I can write this whole thing. I can simplify the notation to a certain extent and say my output image of my system is whatever my input signal is convolved with my point spread function, and that's it. I'm done, right? So I have an input, 2D input. I just convolve that input with one simple point spread function, and there's my output. Right? And that is a simple mathematical procedure. It can get broken up into two independent parts sometimes, and so it makes life a lot easier for computing what's going to happen. So convolution, for those of you who don't remember what convolution is, if I have two functions, f and g, and so here I've just got a rect function, and here's basically a ramp function that has finite dimension, right? To do the convolution of f with g, a couple of things happen. The first thing that happens, because there's negatives up here, these negative signs, this function g flips around, so now it's a ramp going the other way. So I've reversed the x value on it, or the direction. And then as we cycle through offset values in the integral, as we cycle, we're doing this integral, right? So we're going to cycle through these values here in 1D. The function moves across the other function. So g moves across f. And as it's moving across, we multiply the two functions together, as in that equation, and we calculate what is the area under that product. And it produces this curve here. So here we have some area, so we get this orange line. Here there's no overlap, we get a 0. And so as they overlap more, we'll reach a peak once they're maximally overlapped here. And then as it moves off, it comes down. So the convolution of f with g, in this case, looks like this, right? Doesn't look like f, and it doesn't look like g. It looks convolution, yeah.
With the second function again.
That's a really good question, and I don't have a great answer for it, other than we'll work this out, that it actually works out in the mathematics that the behavior of this operator is better when you do this flipping, because you could do it, it's not a convolution, it's a correlation, I think, is when you just do it without flipping. And that too gives you a function that looks something like this, right? But I can't, does anybody know off the top of their head? Yeah. It's the autocorrelation, right? right,
I mean, it's not bad to do it that way, it's just not the way we define it.
right. And it's not it doesn't have the same properties that a convolution has, right?
We'll be back.
Yeah, yeah, just be negative signs everywhere. Yeah,
You have to flip HOT, the impulse response.
Yeah.
Every time you were to convolve it with
right,
any function to get out the output.
Right.
So you just have to flip stuff, it would be a pain.
Is it to maintain symmetry as well, like patch patch with versus correlation and that with patch is same. So is it to correlation as well that we do this like correlation of G with patch and
yeah, I think they're both symmetric, right? They're like F convolved with G and G convolved with F are the same. And F autocorrelation with G autocorrelation is probably the same. So I'll look that up because we'll go down into a rabbit hole here. But there's a good reason. This is like a really short answer that I should have. ChatGPT will give me the answer. Right. Okay. So convolution is something that is used like 5 trillion times a day now, right? Because in your phone, when you take pictures, you don't know Apple's doing this, but they're grinding away in your phone there, like looking through all the faces and going, hey, there's the same face, the same face, the same face. And it's an amazing thing, right? They basically can pick off my kids from like I've got kids who are in their 30s and they'll just nail them all the way down to when they're like 18 months old. Same person, right? Like, huh, well, that's scary, you know? So that's all this deep learning stuff for object recognition, image recognition, dogs and cats and cars and all that kind of stuff, right? And it's done using these convolution networks. And what happens is you have your original picture and they take a kernel, many different kernels, convolution kernels. So this is the H function, H of X. They just start creating a bunch of them, right? And if you look at this one, it's like -1, -2, -1, 0, 0, 0, 1, 2, 1. So this is a ramp, right? So this is, you multiply it on the image and then you pass it across. And basically big numbers are going to come out if there's a ramp right there. So that's what feature this thing is pulling out of the image. And so they multiply the image by maybe 128 of these, 256 of different kernels. And then the output images here are a sequence of output images that they blur and then give that a weighting to the next level, right? And so all of these things are added up with different weightings until finally you get some kind of encoding for this picture, which is a set of numbers, which are these weights, right? As opposed to the actual pixel values, you now have a set of numbers, which are these weights for the convolutions. And you basically train the weights such that this algorithm can say separate cats and dogs, right? Or people and whatever. Yeah.
So from the previous slide, we flipped the convolution, but for like deep learning, we use convolution kernel. We don't flip it, right?
Yeah, you do.
It's something.
We have its autocorrelation. Yeah, but you could just flip the signs of the things. It's not. I don't think it's that important.
But then shouldn't it be called like correlation?
Yeah, it could be. Yeah. Yeah. It's so like you have the ability to set this thing to whatever you want. So I don't know. And then you just pass the kernel across the picture, right? And do those multiplications. So I don't know. Okay.
sorry.
Yeah.
What do you say? Why do you say it's a kernel?
Say again?
Why do you say that matrix is a kernel?
Oh, is a kernel? Oh, I'm sorry. Yeah, that's gibberish. A kernel is if you have a filter, say I want to smooth the signal, usually H of X is called a kernel of the filter, right? So I set an H of X to a Gaussian of a certain width, and then I say, and I'm going to convolve my signal with that to smooth it. That Gaussian I've set up is called the filter kernel, right? So in a sense, when we go back to this, right? You can say, if I can model my imaging system as a big old filter, like signals coming in and I'm just going to filter it, then that's the filter kernel. What's going on?
So it's not the kernel as in mathematics, that thing that takes you to the zero. It's not the same concept. I can't recall.
I can't, we'll have to talk about what that one is because I don't know what you're talking about. Okay, so if you have linear shift invariant systems, simple things start happening such that if I have my input here and then these two boxes represent my system, okay? And H1 takes the signal and modifies it through this relationship, this convolution relationship. And H2 takes the output of that signal and then modifies it again. So for example, if I have stepwise things like the fact that my source of X-rays is not a point, it's a rectangle, that can be modeled as a convolution because it smooths your final picture. So that's one thing that's going on. And then I have an array of pixels that have finite dimension, like they have a certain width, right? That can be modeled also as an integration or a smoothing. So those are two things that are happening, right? If those two things happening are linear and shift invariant, then, so this happens to signal first, then this happens. I'll get exactly the same output by doing this one first and this one second. Doesn't matter what order they get done in, okay? It happens. And if you just want to put it as one big old system, you can just convolve this with this, and then that gives you a new H, which is the convolution of the two, and that's the whole system, right? If your system has part of the signal or the signal goes into one thing and it goes into another thing, and then those two things get added up to make the final output, you can just add these two things and apply it all at once. All right. Okay. Okay, separable systems is another concept which, if you have separable systems, you're in luck because you can simplify your analysis a lot. And I'll get you in a sec. And so basically what it means is if my kernel here or my point spread function is a 2D function, but I can actually write down an equation such that it's the product of two functions that are solely dependent on one dimension. So I have it in this class of functions. Then a lot of things get much easier, right? Because I can do signal processing in one dimension. I can break up all my signal processing into sequences of 1D signal processing. So if I have, I can compute output of my system from the X, direction. So my input image is here. I can compute a convolution of the point spread function in X with my input, right? And then take the output of that, which is WXY, put it in here, and then cross-correlate that, or not cross-correlate. Now you got me going on the cross-correlate. Convolve that with the point spread function that's dependent only on Y, and do that convolution separately to get my final output here. And so here's an example of a very useful separable function, right? Is this function here, right? Which is a Gaussian blob, okay? So this thing here is, it's got a peak in the middle and it rolls off differently in X and Y, but it's a blob and it is completely separable, right? So it's a very useful function. Yeah. Oh, sorry. Yeah. Yeah. Where it's the sum of two things. Yeah, I mean, in say, if you did multi-coil imaging, right? It's the sum of pictures. So in MR, sometimes your input comes in and your your object is making a signal, an RF signal, and you image it differently with different coils. So you get a signal, one comes from one coil, signal two comes from another coil, right? And then you actually add all those up to produce a picture. So that'd be one example. In CT, let me think. I can't come up with one for CT right now, but I'll work on it. That's a good question. So okay. Oh, now I'm starting to think of other things. Okay. Let's go back to this breaking things up into two one-dimensional convolutions because the point spread function is separable. So here's a nice image fxy. We're going to blur it by convolving it with the new point spread function in this case in X, right? And we get this output. So we do a convolution with fxy with this one-dimensional function h1. And you can see in this example, whatever h1 was set to, it has blurred the image, and it's blurred the image only in this direction. Because if you look at this edge, what changed? So you look at the really sharp edge here, and that's all blurred out right here. And you look at the sharp edge up here, and then it's pretty well intact, right? So you've still got a really sharp signal when I look this way. But then after I take the output of this, I take WXY and I convolve it in the Y direction, right? Then that gets blurred out too, right? And so these two one-dimensional convolutions took care of my blurring or change in resolution for this imaging system. And I did it really cheaply because those 1D convolutions are really cheap as opposed to these 2D convolutions. Yeah.
The convolution seems to like blur the image.
It can be, yes, but also you can convolve with a function that, say, pulls out edges, right? So if I have an image that's, looks like this, we can design an H that when I convolve, the only thing left is where I have a very steep edge. And so that'll pull out big numbers. It'll give you a new picture that has very low background amplitude, but lots of spiky edges. Yeah.
It's really helpful if you want to tell where our problems are.
That's correct. If in the old timey days when we used to use linear systems to do segmentation, you would actually oftentimes put it into an edge enhancement function and then put a cutoff, right? So you get all these high signals where edges is, and then you try and put some kind of general cutoff and say, at that height, I'm going to call those things edges. And then you would do something like, now I'll connect all those points and everything inside that is my blah, right? And that worked like 84% of the time, right? That's the problem with all of those algorithms is there was always exceptions where it didn't work and the segmentation failed. Nowadays, most of that stuff is done by teaching networks, like deep learning networks. So you say, okay, find all of the faces, you give it 1 million faces with, correct answers, and it just don't really know how it does it. People are trying to work that out. That's kind of the next stage in AI, I think, is looking and trying to figure out by what mechanism are these engines making this happen, right? And we'll discover it just in time to understand why we are being subsumed in their economy, right? So, okay. Okay, so that was linear shift invariant systems, the impulse response function, point spread function, same thing, how you generate a picture with knowledge of that point spread function, okay? The most important, I think, mapping from one function to another function, right, is this thing called the Fourier transform. And You should know this just for being alive. You should know this, okay? This is, if you're a human, you should know this. That's about it, okay? So basically, if you have this function here that's in space, so you've got some kind of bumpiness in space, you want to figure out what are the composite cosine waves and sine waves that are dominant or that are principally making this function do what it's doing, okay? And in order to do that, that gives you this function, which is, it's a function of spatial frequencies. So this x is in centimeters, say, y is in centimeters, and then these variables are in cycles per centimeter, right? So how many, wiggles per centimeter. And it's a trivially simple looking equation, right? That's one of the great things about 18th century math, or I guess this is 18th century math. Is that right? About right, 17 something or other, is that they really went for these beautiful simplistic things, right? Now, if you look at like high energy physics or whatever, and they write down the Lagrangian for some system, you look at it and go, oh, it's like, what? There's like 900 terms. So here, we've got this trivially simple, lovely relationship, right? So what we're going to do to find out what the Fourier transform is at a specific point, let's set a spatial frequency. We'll say 1 cycle per centimeter in X, 1 cycle per centimeter in Y. Let's figure out what the Fourier transform value is at that point. You set those numbers here, put 1 and 1 right over here. They don't change during this integral at all. And then you integrate over the entire function, multiplying by this phasor while you're doing the integral. And the phasor is cycling through values at a specific frequency that you've set, right? And then the integral pops out, and that gives you the value of the Fourier transform, okay? And it's absolutely gorgeous, the fact that if you have the Fourier transform and you want your function back, right? All you do is do this inverse Fourier transform, which is precisely the same thing, except you take a minus sign away from here, okay? And then you get your function back. And this is what's done in MR. This is the function that is your raw data. You do this, and you get what's in the field of view, okay? Sorry to give away the big punchline of MR. But it's, once you get it, it's like, it does what? It's right? That's amazing. So here's a 1D, so those are a 2D Fourier transforms. We set spatial frequencies in both X and Y. If we look at 1D, here's the integral, right? I've got a function, and I'm going to figure out what its, Fourier components are. If we write out, remember we did the Euler's lovely equation, we can write this out as a sum of sine plus I, or cos plus I sine. So you just write that out here to do this integral. It now makes it slightly more obvious what's going on. Specifically, let's take a look at this component. And I say, okay, here's my gx, and it's some function as a function of x. I'm going to integrate across all of x, right, when I multiply by a sine wave that has this frequency, and I'll do that integral, right? So I'm going to do it for every sine wave, right? I'm going to click up in frequencies and just do it for every single one and see, do I get a number that comes out of this integral that's not 0, right? And so it's sort of like taking your input and saying, how much of this function looks like a cosine of this frequency, and how much looks like a sine of this frequency. If it doesn't look at all like it, the integral will come to 0, right? So here, let's take a look at this function here. This is a square wave, right? So I've defined that. By the way, this output came after I typed 18 words into ChatGPT, something like that. It made this plot. So you can play with this as much as you want. So here's our function. It turns out if we add this sine wave plus this sine wave plus this sine wave at those frequencies, we get this blue line here. And it's, as you can see, though, as we're adding up those things, we're getting closer and closer to this underlying function. We're saying, wow, that's pretty interesting. These are the first, the third, and the fifth harmonic of this thing, right? They're not every harmonic. And why aren't they every harmonic? Well, there's the first, second, third, fourth, and fifth harmonic, right? So if I do that integral, so this is G, this black curve here, and I'm going to do the integration. I'm going to multiply G times the sine wave at this frequency right here. And is that integral going to be positive? So it's this multiplied by the sine wave, right? Yep. Everything's positive. I get a number, right? When I do that integration, right? In fact, if this is 1, I just get the integral under the darn sine wave, right? To that point. So I get a number, right? So let's go to the next harmonic. And we're skipping the partial harmonics here. We're just going to, this is discrete. We're going to go all the way to the next harmonic. Here's a sine wave that's pink, right? So that has a certain K space or spatial frequency. Let's do that integral. I multiply this sine wave times my function, right? Do I get a number? Nope. I get 0, right? Because it integrates to here and this balances that. So it's 0. So I have no component of this sine wave in this function. That's what that's telling me, right? And then I go to the next harmonic, and it's this one that isn't an even full cycle. When I do the integral, I get so much here, and then it goes to 0 by there, right? But then there's a bit left over, and so I get a positive number. It's a number that is less than I got for the full, first harmonic, right? It's whatever the integral is under this. Next one is this. And by now you see the pattern. That goes to 0, right? So the fourth is not in there. And then the fifth is the next one. And if I calculate how many, so I've got 1, 2 that went to 0, and I've got that left. So that much left. So that's how we get the individual harmonics that are part of this, the components of sine waves that add up to this thing, and their amplitudes are given by those relative areas. Okay, that's what that integral does, right? And so when you add these, literally just add those things up, you get when the first two, and then add those two, and you get something that eventually, as you go to higher and higher frequencies, approaches this arbitrarily close to the function. Okay, so that's like that's a visual description of the Fourier transform. If you don't like algebra, a lot of people, they just look at the algebra and goes, oh yeah, I get that. Not me. So yeah.
Back to the picture, please. So there you're showing the calculation of the Fourier transform of the square.
Right.
And the result is the blue.
The result is the blue. When you add up the first, third, and fifth harmonic, right, you get the blue curve. Right. If so this thing here is the sum of the ones that are non-zero, right? And it's approaching the square wave. It just gets better and better as you get higher and higher frequencies. And the amplitude of the harmonics goes down, 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 right? Okay. So Fourier transform is defined as this. In EE, if you did this as an undergrad or whatever, normally you start out where this is time, right? So you have a signal in the time domain. You've got a receiver or some kind of a clamp on a signal, and you watch the time domain signal go, right? And you ask the question, what are the frequency components in that signal? A really interesting signal is if you take a microphone and you put it up and somebody plays a violin, right? You get a time domain signal, right? And then you go over to somebody playing a cello and you get another time domain signal. Those two time domain signals, when you look at them in raw time domain, they look pretty similar, right? And in fact, it's hard to tell which one's which. if you take the Fourier transform of those two time domain signals and you get essentially the frequency components in that signal, you'll get different spikes at different harmonics for those two instruments. And that's how you tell what they are, right? It's like your brain somehow when it listens, breaks down that continuous time domain signal into some kind of spikes that say, oh, that's cello, right? So it's likely that it's doing some kind of frequency analysis, right? Your brain is doing some kind of frequency analysis, more than likely. I don't know. It might be a reach, but yeah,
When you do the Fourier transform, you're transforming your time domain signal to your frequency signal.
correct.
So if you were to do like a Fourier transform on like just a singular sine wave, you just get like maybe a drag delta spike in your frequency, right?
Correct.
So then if you start adding like sine waves together and have this like kind of rectangle function as you had before,
Yep,
then that would break it down into like multiple drag deltas at like each of the different frequencies.
correct.
Okay.
With different heights. Right. Okay, good. And so that's if you're an audiophile, this is a big deal, right? So you look at time domain signal and you ask, what can my speakers produce? So what's the question you ask? Is like, what is the relative amplitude or power coming out of my speaker when I'm looking at a particular frequency? So at 10 kilohertz, what does the speaker produce? At 20 kilohertz and at 30 kilohertz. 30 kilohertz doesn't matter, right? Because you can't hear it, right? You might feel it. I don't know. If you had a real big pop or something like that, you might feel some kind of shock wave at 30 kilohertz. I'm not sure. But usually human hearing goes to about 22 kilohertz, and then you're done. As you get older, you basically hear lower and lower frequencies with higher relative amplitude than high frequencies. So the high frequencies start to go down. And then you have to get people to repeat what they're saying because you can't determine what consonants they're saying. And so it becomes very convenient because you just don't hear people anymore. It's like, eh, whatever, you know. So now what we're going to do in imaging is instead of the time domain, right, our function that we're really interested in is in the spatial domain. Okay, so it's a picture. And so it has sort of oscillations in the spatial domain. And then we ask the question, what are the components that are oscillations in the Fourier domain? And we usually call those K values, and they're in, cycles per millimeter, or cycles per centimeter, something like that. Okay, so some notes about computing these transforms. Okay, so this was the question you asked earlier. If my function here is a delta function, so my image is a delta function, and I compute the Fourier transform of a delta function, what do I get? Well, the answer's right there, so it's not a big mystery. But basically, you get one, right, for every, frequency component. You just have the same contribution, right? So it's independent of frequency. Just it doesn't matter what frequency it is, it's in there, right? And you can imagine a signal that, if we go back to audio, a delta function in time, right? When you're listening, in my generation, we used to listen to like these things they pressed out of vinyl, right? They would press and they had grooves in them. And then you'd put a stylus in the groove and it would vibrate the stylus back and forth, and that would produce a voltage to make the sound. And those things, when you're a kid, you just throw them around and they'd get like imperfections in the grooves. And when it hit an imperfection, when the stylus did, it went boom, and you get a pop, a really big pop sound, right? And that's like a delta function. It just goes. It's just like, no. So it's a very, very, very short, loud signal, right? And it has essentially all components, all frequency components are in there, right? If you shift that delta function in space over here, right, and take the Fourier transform of that, you still get a signal that has a magnitude of 1 everywhere for every frequency component. But in order to shift that signal, you add a phase to the Fourier component as a function of distance or as a function of frequency, right? So you get a linear phase shift. But they're all still equally 1 all the way out to infinity. What's the Fourier transform of? Remember what this is? This is the rect function. So it goes 0, 0, 0 up to 1/2, goes to 1, 1, 1, 1, or negative 1/2. I guess I should draw it this way. Goes this way to negative 1/2, up to 1, then down to 0 again at 1/2, right? And so to do that Fourier transform, it's just the function is just 1, and we integrate between -1/2 and 1/2 because it's 0 everywhere else. And so that gives you this integral right here, right, which you can work out. I leave that as an exercise for you to work out, that this definite integral turns into this thing, right? And this is basically the sinc function, okay? And it's basically sine pi kx over pi kx. So Fourier transform of a rect function gives a sinc function. And here's graphically what that is. Here's a delta function at the origin. It gives you a constant as a function of spatial frequency. The one that's shifted gives you something that has constant amplitude as a function of spatial frequency, but its phase rolls depending on how, and the rate at which the phase changes depends on how far out from the origin it is. And here's the Fourier transform of the rect function again. So here, it's good to have that one in your brain. That's going to happen a lot in MR. This is basic. Oh no, this is important. Okay, I was going to say it's basically the same, but if you took the Fourier transform of a phasor that basically has a specific frequency, that will give you a delta function offset from 0 at that frequency. The Fourier transform of a pure cosine wave, right, in the plane or along x, this is 1D, so along x, gives you 2 delta functions. And one is at k0 and the other one is at minus k0, and they're both positive. So the power gets split between these two. And it's basically a wave going this way and this way at the same speed. And then sine wave, same deal. You get 2 delta functions, except one is positive, one is negative, and it's phase shifted by 2j. That I think. Okay, Fourier transform, important property of this thing. Remember, we're taking functions and making new functions. The input functions, if I have 2 functions and they're a sum with 2 different weightings, I can take the Fourier transform of each individual function and then put that weighting in front of each individual function. So that's they're linear. Same, they're linear in 2 dimensions and 1 dimension. Oh, and then this is you've already probably caught on to this, that the Fourier transform and the inverse Fourier transform are obviously related closely, right? The formula looks almost identical except for that minus sign. So here's our definition of the Fourier transform. If I take the Fourier transform of this function, I get the delta. So it's just a sinusoid going in the plane at this rate a. So I get a delta function. When I take the Fourier transform of that function, I get essentially this one, but with a minus, with the frequency reversed. Okay, so if I just keep taking Fourier transform, so I take the Fourier transform of this, get this, take the Fourier transform of that, I get this back out. It's not exactly the same function. It's the k variable has been swapped or inverted, right, in sign. Okay. So basically the easiest way to remember that is the Fourier transform of this thing is the original spatial function at minus kx. Okay, so you have to swap the independent variable. Okay. So let's make sure you understand what's going to happen. This thing is the Fourier transform of the original little gx in here, or little gk, I should say. So I've got a little gk, take its Fourier transform, I get g of x. Take the Fourier transform of that, I get back little g of minus kx. Okay, I should have put more steps in here. So applications. Okay, so here's a good application. In that, if you're asked, here's a complex function, it's a sinc function. What is the Fourier transform of that? It's on an exam, right? You say, your prof says, what's the Fourier transform of this? Or they just put this in, say, evaluate this integral, right? That's a good question. So you look at that integral and go, what? I got a 1 over x kind of thing happening. I got a sine wave kind of thing happening. I got this complex function phasor, all that stuff. So, but we know, since we've taken this course, that this is just, the Fourier transform of that thing, which is a sinc function. And we know what the Fourier transform of a sinc function is, right? It is a rectangle, right? So we now know that I can say the Fourier transform of this thing, the sinc, is the rectangle at minus kx. So it's the rectangle switched, like rotated around the origin such that x is now minus x. But that also equals rectangle of x, right? It's a symmetric function, so it doesn't matter that we did that switching. Okay. So this duality thing is really convenient. The fact that if I'm working in space, in Fourier space, if I know that something is going to happen easier in one of those spaces, I can just flip over there and do an operation in that space and then Fourier transform back, right? So knowing those two spaces is important. So inside the textbook, you should probably know all of these, I think. Yeah. These are just in your head, you should have all of these transforms, right? And it seems like a lot to begin with, but it's not really a lot. So 1 gives you a delta function. Fourier transform of delta function gives you 1. We know that. That's duality right there, right? Here's a delta function offset, gives you a phasor, right? At the frequency of the offset. Remember, this function is it's a continuous function of x and y, where we have delta functions separated by delta x, delta y. So it's a comb in the xy plane. Remarkably, when you take the Fourier transform of that thing, you get a comb in the Fourier domain. Okay, so a comb, or these set of delta functions, maps to a set of delta functions. And that's going to become very important when we think about things like aliasing and sampling and stuff like that. So this is essentially the dual of this up here. Okay, what else we got? A sine wave, plane wave in the plane gives you delta functions in the plane, right? So if I have a plane wave, sine wave at some angle, I'm going to get delta functions at points in the two-dimensional Fourier space that are essentially along that angle, right? Is that rectangle we did, sinc, these are duals, comb we just talked about, and a Gaussian, and this is lovely. Fourier transform of a Gaussian blob is a Gaussian blob, right? So and we might do that as a problem. I don't know if we do that as a problem. Those are really, just remember all those. And well, it's only really half of them because the duals are all in there. You switch sides and it's the same thing. Okay. Now we talked about some of these properties. One important property of Fourier transform is it's linear. So if I have these two functions and my final function is the sum of them, then the Fourier transform is just the individual transforms times the same coefficients. Translation, we saw that we take, if I have a function and then I translate the function in my field of view, my Fourier coefficients don't change in magnitude, but they do change in phase, right? As when I look at the magnitude of my Fourier coefficients, it stays exactly the same, but I get a phase shift from that translation. Conjugate, so if I have a function and I take the Fourier transform of its complex conjugate, that I take the Fourier transform of the function and I take the complex conjugate, but I reflect it around the origin. So u goes to minus u, nu goes to minus nu. Okay, so it gets reflected around the origin. If there is no complex part, if it's a real valued function, then I know that the Fourier transform is conjugate symmetric. That means that I take just because this is a real valued function, when I take the Fourier transform, it's a complex function. It has phase at each point. But I do know that there's this symmetry in the function, in that if I reflect around the origin, the complex conjugate is just the reflection around the origin, right? What else do we have here? Signal reversing, well, that's pretty simple. That just comes from this up here, minus x minus y. Scaling, this is very useful. So if I change my coordinates with scalar variables here, then I take my original Fourier transform, I have to divide the spatial frequency components by these scale factors, and I have to normalize the whole thing out front in order to get the correct Fourier transform. And circular or rotation. So this is a great property, and you can just remember this in your head. If I have a function, an image, and I rotate the image like that, then when I look and say, what happened in Fourier space, the Fourier transform just rotated the exact same angle. Okay, so it's in space and you rotate, Fourier transform rotates. Okay. That's very useful in MR, a lot. We did convolution, so we know that. Did we do the product? I'm not sure we did that. Maybe we didn't. No, we didn't. Okay, this is going to be really important. We're going to talk about this right now. Okay, in that, well, I'll just give away spill the beans. If I have one function and I convolve it with another function, when I take the Fourier transform of that final function, f convolved with g, I can just multiply the Fourier transform of f times the Fourier transform of g. This is probably where that negative with the convolution is important versus the cross correlation. It's probably right here, in that this is a very simple theorem, right? In that convolve these two functions in space, which is a kind of a complicated integration kind of move. In Fourier space, you just take the two Fourier transforms and multiply them. And that's pretty trivial, right? Multiplying two functions together. Okay. Separable functions, if you have a product of two functions that are in different variables, then you just multiply their Fourier transforms, right? In those two spatial coordinates. And this is called Parseval's theorem, which means the total power under your image is equal to the total power under the Fourier transform, right? So if you take, these are complex numbers. If this is a real number, these are complex numbers, but if you take the magnitudes and integrate this thing, you get the same number on each side. That means the Fourier transform doesn't make extra power or extra signal, right? You've got the same amount of signal power in the Fourier domain as you do in the spatial domain. Okay, so let's do, what time are we at here? We got 10 minutes? Okay, great, thanks. So this is probably the most important theorem for MR, I would say. And that is that if you convolve something in the spatial domain and take its Fourier transform, you can just multiply it in the Fourier domain. And this is where modeling our system as so remember, if this was our input to our system, and this is the point spread function of the system, right? H is now the point spread function in this thing. Then I just look at the, Fourier transform of my God-given object, right? And I multiply it by some function. And that's what my imaging system does in the Fourier domain. It just multiplies it by some function. This is often called a filter, right? So if I convolve to make, say I have g of x and it's very noisy and I want to smooth it out a bit, so I convolve it with a Gaussian to smooth it out. That's equivalent to taking the original spectrum from my g of x and multiplying and reducing the high frequencies in that signal by, in the Fourier space, multiplying by this filter, right? So in MATLAB or any other package like that, when you say, please convolve this function with this kernel or this point spread function or this impulse response function, please do that convolution. MATLAB usually does not do that convolution, right? It doesn't do those integrals. It takes Fourier transform, multiplies it once, inverse Fourier transforms and gives you the answer, right? Because it's so much more efficient, right, than doing all of those integrations, right, in the original convolution. So that's why this theorem is so darned important. And many of the artifacts that you see in MR, if you know what's going on, if you look in the Fourier space at your data and say, what's happening here? The fact the Fourier transform is linear, stuff that adds up in the data also adds up over here. A multiplication of some windowing in your raw data, you know what that's going to do in your image. So it's very useful to be able to look at the raw data space and pull out some of these things that are happening. So for example, you can multiply your data by, the top hat function such that every other data point disappears, right? Say, well, what does that do, right, in your Fourier space? So, so the system modulation transfer function, you can imagine, is what this guy is, basically, right? So here we've got our image. This, let's call this our impulse response function. When we go into the Fourier domain, we have the original God-given spectrum of the signal that is coming into the system. And this is the modulation transfer function. And it normally has a shape that looks something like this, in that high frequencies get attenuated, right? And so we multiply by that, saying this rolls off, we multiply that, and then take the inverse Fourier transform. That gives us our result of our imaging system. We obviously want MTFs. That an ideal one would be 1, 1, 1, 1, 1, 1, 1, right? Past all frequencies equally, right? And that, if that was the case, so if we had an MTF that was 1, 1, 1, 1 everywhere, right? What's the inverse Fourier transform of 1, 1, 1, 1, 1, 1 everywhere? It's the delta function, right? We just did that. So you go back and we have the delta function. Therefore, at this point, this would be a delta function, right? And then the system wouldn't blur anything, right? No imaging systems are like that. They can go out there for a while, but eventually they start rolling off. And you would prefer to have a system that's out here that doesn't roll off the high frequencies as much. And then if you have that system, then you have the choice when you're presenting the images to, say, a radiologist who wants to read them, you have the choice to multiply by any of these other filters to make it look smoother and the noise and reduce noise, right? If you present images that have a spectrum like this, sometimes the radiologist says, there's too much high frequency hash in this scan. Like noise comes in at very high frequencies often, right? It looks like, it's sonically when you have headphones and there's like electronic noise, it's like that's high frequency stuff coming in through there. On your TV, none of the TVs you guys have ever seen, but in the old days when you used to have antennas and amplifiers and all that, you'd have noise that would come in. It would be like speckly white and dark pixels on your television, and that was like white hashy noise, right? Nowadays, I love when my digital TV breaks, it just bizarre things like it goes and there's like an infinite number of ghost images all of a sudden come over it. It's like, what the? But actually, here's a really interesting aside. If you have an old TV and you turn on, you put the antenna up and you look at the noise that just comes out, don't go to any channel that has a signal, go off somewhere that doesn't have a lot of signal. Just like turn it on. So you get all this noise field. Apparently 25% or 20% or something of the power of that signal is the cosmic microwave background. Oh, that's so cool, right? That's radiation that's been traveling for like 14 billion years before it hit your antenna and went, So that's the other thing about when you see a star, like say it's a star, the stars you see with your eyes are normally like, a light year away or something. They're not like millions of light years away. Well, you can see Andromeda, right? It's like a million light years away, something like 2 million. So say you're looking at Andromeda, and then this photon goes ding, and causes a little spark in your brain. And you go, oh, sorry, man. That photon's been traveling for like, 2 million years. It's like, whoa, I'm gonna make it. Boom. Oh, hit that guy. Okay. So here, let's look at these two-dimensional MTFs. So here's our original signal and say this is its Fourier transform. Normally, when you look at the Fourier transform, like if I'm looking at that, to me personally, it doesn't have as much information as this does, right? Just my own feeling. However, it's all there, right? Well, mostly it's all there. It's just you don't know how to read it, right? So when you take the inverse Fourier transform, we get this. Well, let's do this. Let's multiply by a big H that rolls off, right? The frequencies out here. So the relative amplitudes of the Fourier components that we're going to inverse Fourier transform are given here. When we go back, we get a blurred version of this because the information out here to create edges has been, basically multiplied down by a filter. And then if I just look at the inner core of the Fourier transform here, and all this is 0, then I get a very blurred version of that picture. Yeah.
We apply filters to the image generated by the Fourier transform.
Sure. Do you want but once these, like this filter here, so you can multiply by h of x, and so now I've got 0 out here, right? And I look at this picture, I can start doing things like say, oh, I should edge enhance this. And that will push some signal back out into these spots, but it's signal you're just guessing at, right? Once it's gone, once you've multiplied it down, it's gone, right? So you can make intelligent guesses as what should be out there, right? And when you take pictures and you see them restored such as edges are there, that's because there's some intelligence as to what signal should be put back. Yeah.
Picture on the left top, it just looks like it contains the most information, so where to read it, right?
Yeah.
Why would it apply filters to this?
That is a great question. Like, if you could have this picture, why on earth would you ever have this picture? Like, what is the point, right? So the point is, to get this picture might take me 48 seconds. To get this picture might take me 4 seconds, right? So I could get a whole ton of these pictures really fast, right? And let's make this 4 seconds and this 40 milliseconds, right? So now the question is, if I can get a picture every 40 milliseconds, what else can I do here? I can look at how signals change on the order of 40 milliseconds, right? So that's one way you could say, oh, maybe if I can get that data that fast, I know it's blurry, but I can see what's going on temporally. And so there's all these trade-offs and then here you assume the person doesn't move at all, right? And if it takes an hour to get that image, that's highly unlikely, right? They've probably shifted around and stuff, and so you're going to get blurring from other factors, right? So that's why, yeah.
Start the image on the right from the, or sorry, to the, on the left from the right.
If you can do that, you get the Nobel Prize. No, it's true. It's true. Like, what is in here? So basically, all of these are 0, right? But we do have all of these, right? And the question is, how do I figure out what all these points are just from these points? Can I do that? It depends, right? I mean, the answer is it depends. And if this was an image of 3 circles at different locations, and I knew it was an image of 3 circles, then how many numbers do I need to reconstruct that image? Like a dozen? I need diameters, positions, amplitude. So really, yeah, I just need a few numbers, right? So I should be able to do that. However, this is not just a set of circles in the plane, right? There's other stuff. However, prior information as to what you expect to see is really important. So one thing you could do is every once in a while, you take a picture like this and then take these very quickly. And when you see a little red blob here, right, in the temporal information, say, well, where the heck is that? I go back to this one, right? Or you could just impose on top of this one a color scale that is derived at this resolution, but sits at the right location spatially, right? So there's a whole bunch of ways to connect stuff. But actually coming up, if you only have this, coming up with this is pretty tricky.